All right, class, welcome to Math 1030, section unit number 2B, extending unit analysis. So we're extending our unit analysis from 2A, so we're just doing some more unit investigations. Go into more detail. First we do a exponents review. In the homework and in the book they talk a little bit about this, but it's just a couple of basic rules. So we're going to start with, in number 1, we have some problems that practice the product rule for exponents. And the first one is 10 to the 5th times 10 to the 3rd. And that's going to equal, essentially, we have 5 tens multiplying themselves. That's what 10 to the 5th means. Okay, so there's 5 here. And then I'm going to continue on by multiplying 3 more tens. Okay, that's my 10 to the 3rd. Now notice that exponents are repeated multiplication, and so I have 5 tens here that are multiplying themselves, and 3 tens here that are multiplying themselves. And so in total, I have 8 tens multiplying themselves. But notice that 8 is also the sum of 5 and 3. Okay, so we can also do that 10 to the 5th times 10 to the 3rd is still the same as 10 to the 5th, 5 plus 3. Add the exponents, you get 10 to the 8th. Oops. Okay, so this is our shortcut right here. We add our exponents, and then we get our answer, 10 to the 8th. Let's go ahead and extend that to the next one. B is going to be 10 to the 7th times 10 to the negative 4th. Extending our shortcut rule, we have 10 to the 7 plus a negative 4, adding the exponents because they have the same base. And we have 10 to the 3rd. Part C, 10 to the 8th times 10 to the negative 8th. Okay, so we have 10 to the 8th plus a negative 8 gives me 10 to the 0 power. And we know that that's all 1. Okay, so we have 10 to the 8th, 10 to the 3rd, and 1. Next one is quotient rule. If you have 2 exponents that are dividing themselves, you subtract their exponents. 2 powers dividing themselves, you subtract their exponents. Well, we have 10 to the 9th divided by 10 to the 5th. So that's 10. Oops. Okay, so there's 10 to the 9th right here. And then 10 to the 5th is right here. So if I want to simplify these, I can take them out as pairs by making them ones, okay? So this pair becomes 1, because 10 divided by 10 is 1. This pair becomes 1, that pair becomes 1, that pair becomes 1, that pair becomes 1. So when you have all the 1s multiplying themselves, then they will essentially be just 1 or itself, okay? And when you do that, you're left with, all of those 1s go away, and you're left with 10 times 10 times 10 times 10, which is equal to 10 to the 4th. Now notice that the 9 and 5 are related to 4. So what I can do is I can say that that is 10 to the 9th, or 10 to the 5th, is equal to 10 to the 9 minus 5 power, which is 10 to the 4th. Okay, so there's my little shortcut there. All right, let's go on part E. We have another one to practice. 10 to the fourth divided by 10 to the negative third. Okay, so by our quotient rule, 10 to the 4 subtract a negative 3 is 10 to the 4 plus 3, which is equal to 10 to the 7th. In part F is not either the quotient rule or the product rule. It's just going to see what you think of 10 to the 5th plus 10 to the 3rd. Now 10 to the 5th is 10 times itself 5 times, and we're going to actually write it out as an answer is 100,000. Plus 10 to the 3rd is actually 1,000. When I add those together, I get 101,000. Okay. So reviewing of exponents. Okay, going on to number 2. Our handout. In part number 2, we are looking at standard units. What are they and why are they helpful? Well, standard units could be like inches or centimeters or anything that everybody uses, okay? So standard units are units that have the same meaning. Have the same meaning for everyone. Why are they helpful? Well, that's why they're helpful, is because they have the same meaning for everyone. Helpful. Okay. Number 3. What is the U.S. customary system? The U.S. customary system is the system that of standard units for lengths, weight, and volume used in the U.S. Okay, we have inches, we have pounds, we have gallons. Those are all examples. Inches, pounds, and gallons. Okay, all of those are in the U.S. customary system. Okay, and if you want to see a whole list of the customary system, look to page 89 in your textbook. So number 4, what is the international metric system? Okay, it's actually an international system that is a system of standard units for lengths, weights, and time and volume that's used in the rest of the world. So we call it the metric system. So a system used in the rest of the world for lengths, weight, or mass, volume, and, well, there's one more, time. Time is measured with the metric system, but it's actually, there's no U.S. customary system for time, so time is actually used everywhere in the world the same. Okay, so lengths could be centimeters, weight could be grams, volume is liters, and time like seconds. Okay, so that's the metric system. And for a table of the metric abbreviations and how they convert between themselves, see page 91 in your text. There are 2 ways that the metric system simplifies measurement systems, and that's what goal was, is that the U.S. customary system, which is derived from like the English system, very, very old European system, had a couple of flaws. Like a foot Could be whose feet. So named after someone's foot, but is it the buyer or the seller's feet? Okay, so the first main goal was to use a few basic units. And then the second goal was to simplify conversions by using base 10 system. Because that's the number system that we use. And they didn't want to think about like, well, 12 inches in a foot or 5,680 feet in a mile, those types of things, 16 ounces per pound. They wanted to simplify everything by using base 10, okay? And they were pretty successful at it. All right, next part of our handout is going to be doing some conversions. So in unit 2A, we did conversions within the systems, but in this one, we're going to convert across systems, okay? So that's what number 5 is about. So part A, we want to convert 25 liters and see how many quarts they are, okay? So we're going to take our 25 liters, put over 1. Now, in these conversions, and throughout this whole section, I use conversion factors, okay? Because this makes all the calculations easier, and we can actually string them together. So 25 liters is equal to some number of quarts, and so I look at page 93 for a table of all the US and metric conversions between systems. Okay, so look at page 93 for all of these. And on page 93, I have one, and I want liters to cancel, so I put liters at diagonals of each other. And 1 liter is 1.057 quarts. Okay, so my liters are going to cancel, and I'm going to have, when I multiply 25 by 1.057 with my calculator, I have 26.425 quarts. Okay, so part B is I'm taking 25 meters and I'm going to set and find out how many feet that is. Okay, and I'm going to use my conversion again, 25 meters over 1 times, and on my table on page 93, I have 1 meter is 3.28 feet. Okay, so I want my meters to cancel. Meter, canceled. Okay, and so when I multiply 25 by 3.28, I get 82 feet. Part C, I have 25 pounds. Okay, I want to see how many kilograms that is. Okay, so 25 pounds equals a certain number of kilograms. So 25 pounds over 1 multiplied by, well, the conversion factor for pounds and kilograms, we have 1 pound for every 1 or 0.4536 kilograms. Okay, and so my pounds will cancel and just have kilograms. When I multiply 25 by 0.4536, I get 11.34. Okay, part D, I have 25 miles is equal to a certain number of kilometers. Okay, so my 25 miles, put over 1. I want miles to cancel, so 1 mile, I put in the denominator, is 1.6093 kilometers. Okay, so I cancel my miles, and I set that, and I do 25 times 1.6093, and I get 40.2325 kilometers. Okay, so looking at my table, referencing my table, part E, 25 kilometers squared is equal to a certain number of miles squared. Okay, these are good for what we're going to talk about later about density. Remember, people per square kilometer or square mile. Practicing this conversion, there's going to be a little bit more to that because they're square units. And I'm going to write down my 25 kilometers squared, put over 1. Now, the table only has miles and kilometers. So I'm going to put down 1 kilometer here is equal to 0.6214 miles. But I want to cancel with the kilometers squared and kilometers. And so I can't cancel right away because I have 2 sets here and just 1 set of kilometers here. So I need to multiply by another conversion factor, the same one, which is the most helpful. So I can go ahead and cancel kilometers here, and these 2 sets of kilometers there. Okay. And what I will get is something in miles squared because I have miles here, and that will give me my miles squared. But at multiplying the numbers, I get 25 times 0.6214 times 0.6214. And on my calculator, when I do that, I get about 9.65 miles squared. Okay. And F is our last one. Oops. Conversion for the section. 25 miles per hour is equal to some number of meters per second. Okay, so I'm going to use my conversion factors again. 25 miles for 1 hour. Okay, I'm going to look at converting not just the numerator but also both at the same time. I'm going for meters per second, so I need to choose which one I'll go for first. Will I go for meters first, converting miles to meters, or do I convert hours to seconds? And I'm going to choose going to meters. Okay, so in my conversion table on page 93, I have 1 mile is 1.6093 kilometers. But I don't want exactly kilometers, I need meters. Okay, so I'm going to need to change my kilometers to meters. Now my miles are canceling, okay, but I need to cancel my kilometers and change them to meters. So I'm going to put 1 kilometer here. And I know that 1 kilometer is equal to 1,000 meters. So I'm multiplying that there together. What's great about conversion factors is now I can go ahead and keep stringing them together, and I'm adding on hours. I need to change hours to seconds. Okay, so hours is at the denominator here, so on the actual part here. Oops. Okay, and so I need to cancel with 1 hour and 60 minutes here. My plan is to go from hours to minutes, then to seconds. So 60 minutes, converting the minutes to seconds here. 1 minute for every 60 seconds. Okay, and as I cancel these units, let's double check. I have, I want meters per second, so I have my meters there in the numerator. My hours will cancel from here to here. Okay, so it's a long ways. My minutes will cancel from here to here, and I have seconds in the denominator, so I'm doing good there. So now I need to do is multiply all the numerators and multiply all the denominators. And when I do that, I multiply 25 times 1.6093 times 1,000, divide that by 60 times 60, which is actually 3,600. And when I do that, I get 11.1 meters per second. Okay, so 11.1 meters per second. Okay, going on to number 6, standardized temperature units. So number 6. Now temperature has been standardized by water. Water plays a big role in our measurements because it's the most plentiful liquid in the planet. Okay, so what is the standard temperature for freezing water in both Celsius and Fahrenheit? And so these scientists have been studying water and what it freezes and the temperature that it boils. Okay, so we're going to start with freezing right now. So we need the water freezing points. For Celsius, it is 0 degrees Celsius, 0 degrees Celsius, And for Fahrenheit, it is 32 degrees Fahrenheit. Okay, so that's part A. Part B, we have boiling points. So the water boiling points. Okay, water boiling points are 100 degrees Celsius and then 212 degrees Fahrenheit. Okay, now we must take in consideration that this is all at sea level. As you go higher in elevation, the lower those boiling points and temperature and freezing points are. So that's all at sea level. Now we have these 2 points on, I'm going to actually make a graph here and draw 2 lines. Now 0 and we have 0 degrees Celsius, and then that's the Celsius one, and the freezing is at, and that's on that 32 degrees Fahrenheit. Okay, so, and then we're going to go ahead and draw a Celsius one line, which goes up like this, and the boiling point is at 100 degrees. Okay, and here is 212 degrees. Okay, so that's the Celsius there. So for freezing point 0, boiling point for Celsius. Okay, freezing point, boiling point for Celsius. Freezing point is at 0, boiling point is at 100. Okay. This line will go on forever like that. For Fahrenheit, the freezing point is at 32, the boiling point is all the way at 212. Okay, so that will go this way. Okay, so there's all ranges in between for temperatures. Okay. All right, so we can have any temperature along these 2 scales. They'll actually meet down here at negative 40 degrees. So negative 40 degrees is not either Celsius or Fahrenheit, they're the same, okay? But all the way in between, as we go up and down these scales, they have certain temperatures, okay? And one temperature for Celsius is the same is a certain temperature for Fahrenheit, okay? Or we can have like room temperature. Let's pretend that this is room temperature. We can have a room temperature here and then a room temperature here. Okay, so they can go to different parts here. Okay, so that's a visual of those 2 temperature systems. Now, what we need to do is we need to convert. Okay, what is a conversion formula? So we're on part B now. Part C, that is. What is this conversion formula from Celsius to Fahrenheit? So if I have a Celsius temperature and I want to convert to Fahrenheit, we take our Celsius temperature, multiply by 1.8, and add 32. So we're going to convert 37 degrees Celsius to Fahrenheit, degrees Fahrenheit. Okay, so the Fahrenheit degrees is equal to 1.8 times 37, which is the Celsius degrees, plus 32. Okay, 1.8 times 37 plus 32, so 1.8 times 37 is 66.6, and that's equal to 98.6, sorry. Okay, degrees Fahrenheit. Okay, so that's actually body temperature, 37 degrees Celsius, and that is equal to 98.6 degrees Fahrenheit. Okay, part E, what is the conversion formula from Fahrenheit to Celsius? So if I have a Fahrenheit, I need to find the Celsius. I subtract 32 from the Fahrenheit, divide by 1.8, and you get Celsius. Okay, so let's go ahead and convert 75 degrees Fahrenheit to Celsius. Okay, so our Celsius is equal to 75 degrees, or 75, go ahead and drop our units for a sec, minus 32 divided by 1.8. 75 minus 32 is 43. Divided by 1.8, you get approximately equal to 23.8 degrees Celsius. Okay. So those are our answers for these sections here. Okay, so 23.8, about 24 degrees is, 25 degrees is room temperature. That's why we studied that one. All right, moving on in our handout, we're thinking about number 7. Okay, number 7 is about energy and power. Okay, units of energy and power. All right, in part A, what is energy? So energy is what makes matter move. Or heat up. What is a calorie? A calorie, capital C. A measure of energy our bodies draw from food. So what is a little calorie? Well, the little c calorie is the same thing, but it's actually 1,000 of them put together is equal to 1 big calorie, big C calorie. Okay. Typically, humans draw about 2,500 big C calories from their food. Now, what is a joule? It's Joule, okay, is a metric unit for energy. Well, how are they related? Well, your calorie from like your 2,500 calorie diet or 2,000 calorie diet, that big C calorie is equal to 4184 joules. And what is power? This is part E. Power is the rate at which energy is used. Okay, so power and energy are very widely confused. So energy is what makes matter move. Power is the rate at which energy is used. Okay? A rate. So it's like a speed, things like that. Part F, what is a watt? Now a watt is the metric unit of power. Okay, so a speed, it's like a rate. 1 watt is equal to 1 joule per second. Okay, 1 joule per second is a watt. Okay. Now we have our exercise bike example. Okay. As you ride the exercise bike, the display states that you are using 300 calories per hour. Are you generating enough power to light a 100 watt light bulb? Notice that 1 calorie is equal to 4184 joules. Okay, so we're starting with our 300 calories per hour, big C, and we're going to change this to watts so that we can see if we can power a 100 watt light bulb. Remember that the rate at which the light bulb is using power is 100 watts or 100 joules per second. Okay, so that's the energy it's using. So 300 calories for 1 hour. Convert those to joules. 4 to 184 joules for 1 calorie. Big C calorie. Now we're going to go to from hours to seconds. So we need to get joules per second to get our watts. Okay, joules per second. So we're going to convert our hours to seconds. And so we could do 1 hour in the numerator for 60 minutes in the denominator. Multiply by 1 minute for every 60 seconds. Oops. Yeah, that's it. And then we'll get to our seconds because these will cancel hours and hours here, calories, calories, minutes and minutes. So we have joules, seconds left, okay? And to get the number of joules per second, we multiply the numerators and denominators. So 300 times 4184 divided by 3600 gives us about 349 joules per second, okay? Which is equal to 349 watts. Is that enough power for a light bulb? Surely. 103, you can actually power 3. That's enough for 3 100 watt light bulbs. Okay, if you keep pedaling at that rate, where you'll use 300 calories an hour. Well, what is, part H, what is a kilowatt hour? A kilowatt hour is a unit of energy. Okay, so remember watts was a power unit, but if we multiply watts by hours, we get back to energy. Okay, so it is a unit of energy. 1,000 watts times hours. And when you do that, you get a lot of joules. Okay, so when you're doing 1,000 watts. Okay, so that's equal to, because you have hours in there too, 3.6 million joules. Okay, so when you do this, we can power light bulbs. So powering a light bulb. So Roman numeral I, your utility company charges 14 cents per kilowatt hour of electricity. How much does it cost to keep a 100 watt light bulb on for 1 day? Okay, so we have 14 cents per kilowatt hour. Okay, all right, so we're going to calculate the 100 watt light bulb cost. Okay, it's the cost for 100 watt light bulb to go on all day. Now when we do this, we need to take our watts and convert them to kilowatt hours. Okay, because our cost is 14 cents per kilowatt hour. So our 100 watt light bulb, put the over 100 watts, which means it has 100 joules per second. Okay, so it's a rate times 1 kilowatt hour, 1 kilowatt over 1,000 watts. Okay, so we are changing our watts into kilowatts because we want kilowatt hours. And we'll go ahead and multiply by the hours that we're going to be turning it on. Okay, so when we do that, our watts will cancel. And we are going to multiply it by the amount of time it's turned on. And that's 24 hours. Okay, and so when we do that, our units are kilowatts, hours, kilowatt hours. And so to find out how many kilowatt hours that is for having the light bulb on all day, we multiply the 100 by the 24 and then divide that by 1,000. Okay, so when I do that, that's approximately equal to, well, it's actually exactly equal to 0.6 kilowatt hours. Okay, now we're going to multiply the kilowatt hours times our rate of paying the electric company. So we have 0.6 kilowatt hours over 1 multiplied by 14 cents per kilowatt hour. Okay, and our kilowatt hours will cancel. And we have 0.6 times 14, which gives us 30. Oh, dang it. Okay, so what we did was we just had a slide mix up here, which we're going to go ahead and back up just a tad. And it's right here. Okay, 100, I was talking about 100 watts, miscalculated it. 100 watts, oops. Okay, so we have our 100 watts right here, times our 24 hours, divided by our 1,000 watts. And that doesn't equal 0.6, it actually equals 2.4. So I messed up on that one. Okay, 2.4 kilowatt hours. Okay, so we're going to go ahead and multiply to see how much it costs to run our light bulb all day and using 2.4 kilowatt hours of energy. Okay, so we're going to do 2.4 kilowatt hours multiplied by 14 cents per kilowatt hour. And when we do that, kilowatt hours cancel. And we get 2.4 times 14, which is about equal to 34 cents. Okay? So it's cost 34 cents to run your light bulb all day long. All right, now what we're going to do is we're going to do part number 2, Roman numeral 2, and it will be how much do we save if we use an LED light bulb, energy saving light bulb, for running the same amount of time all day long, and our energy saver light bulbs has the same amount of light for only 25 watts. Okay, so we're going to do calculate the number of kilowatt hours a 25 watt light bulb takes up by going all day long. So 25 watts over 1 multiplied by we need to do kilowatts, and so we have 1,000 watts to cancel, and 1 kilowatt. Okay, so these will cancel. And when we do that, we get, and we're going to multiply that by, don't calculate that because we can do it for the all day long, so how many hours we're going to use. Okay, and then we have, that's equal to 0.6. This is 0.6 kilowatt hours. Okay, so I multiply by 25 times 24 divided by 1,000. And that's how many kilowatt hours you use. And so notice how the big difference is in 2.4 kilowatt hours versus 0.6. But let's look at the money. Okay, we have 0.6 kilowatt hours over 1 multiplied by my 14 cents per kilowatt hour. Okay, and that's going to be equal to 0.6 times 14 is about 8.4 cents to run that all day long. All right, last one is number 8. We're going to talk a little bit about units of density and concentration. Density, concentration. All right, so A, what is density? Density is a term used to describe compactness or crowding. So how dense something is, how compact things are, how much are crowded, like as in population. So the population density example, if one country has a population of 500 people per square mile, and another has a population density of 300 people per square kilometer, which country has the higher population density. Okay, so my population density problem says that country A, the first one, has 500 people per square mile. Okay, country B has a population density of 300 people per square kilometer. Now these units for population density are not comparable because we have square miles and square kilometers. So what we're going to do is we're going to convert one of them to the other. And let's go ahead and do country B, convert that kilometer squared to mile squared. Okay, so we're going to go 300 people over 1 kilometer squared per kilometer squared. Multiply that by a conversion factor. So I need to get rid of my kilometers squares and change them to miles squared. I don't know what kilometer squared and mile squared conversion factor is, but I do know miles and kilometers from page 93 in our book. So 1 mile is equal to 1.6093 kilometers. Okay, and what this will do, this will get rid of one of the kilometers. Because I have 2 here, I have 1 here. Okay, and so I need to multiply this by another conversion factor, 1.6093 kilometers for 1 mile. Okay, and when I do that, I can go ahead and cancel my kilometers, those 2 kilometers there with those 2 there. Okay, and so I end up with people for miles times miles, or miles squared. So that works out nice. In order to find that answer, I take my 300 and I multiply it by 1.6093 times 1.6093, and I get about 777 people per mile squared. Okay, and so what we're doing is we're comparing the country A with 500 people per mile squared to 777 people per mile squared, and country B has the most population. Okay, going on to another topic, C, which is concentration. Well, what is concentration? Okay, the concentration in this sense is a term used to describe the amount of one substance that is mixed with another. Okay. All right. So here's our example. So part I, just one I. A 5% dextrose solution contains 5 milligrams of dextrose per 100 milliliters of solution. So we have some amount per solution. How many milligrams of dextrose in 900 milliliters of the 5% solution? Okay. So what we need to do is we need to use a proportion. We can. There's other ways probably to do this, but what we're essentially finding is that this is our concentration. 5 milligrams per 100 milliliters. Okay. And we want to know how many milligrams of dextrose is in the 900 milliliter solution. Okay, so we can use that same ratio and set it equal to another ratio where we don't know the top milligrams, but we do know the bottom milliliters. And to solve this proportion, we just cross multiply. Okay, these cross multiply, these cross multiply. Okay, so 100x is equal to 4,500. Okay, that's what 9 times 5 is. Divide by 100 on both sides. And therefore, x is equal to 45 milligrams. Okay, so if you have a 5% solution and you need 900 milliliters of the same solution, you need to put in 45 milligrams of your dextrose. Okay, so Roman numeral 2. Last problem here. How many milliliters of the same solution should be given to a patient needing 100 milligrams of dextrose? Okay, so we have 5 milligrams per 100 liters of milliliters, that is, of solution. We know that the patient needs 100 milligrams of the solution, but how much water should we put in there? Okay, so we don't know the number of milliliters here. Again, we can use a proportion, solving it by cross multiplying. 5x, so these two right here, are the same as those two there. 5x is equal to 100 times 100, which gives me 10,000. Divide by 5, x is going to equal 2,000 milliliters, or 2 liters, right? So if you need to get in 100 milligrams of the dextrose, using the 5 milligram per 100 milliliter solution ratio, you need to get in 2 liters of the solution. Okay, folks, that's all we have. I think that should be good for the homework. There's a couple of trickier ones. Please let me know if you have any questions. Thanks for watching the videos, and hope you have a great day.